Hi guys, today we're doing the topic 3 remediation for Algebra 1, all about relations and functions. So our very first question gives us this table of values, like an x and y table, and we're asked to find the domain and range, and then we want to classify whether it's a function or not. When I think of domain, I'm thinking about all of the x values of a function, and we're going to write it as a list using one of our curly braces, and I'm just going to use 3, 5, 7, 8, and 11. So I just took all of my numbers that I saw and I wrote them as a list. Similar to our range, or our domain, our range is when we think about our y values. I guess it's important to note that maybe we should write them from smallest to largest is what we normally do, and you don't include any repeated values. So see how both of these have 7s, or there's 2 7s? I'm only going to write 1 7. So my range is 6, 7, 9, and 14. Now, to classify something as a function, we are going to look at the domain. So the domain is going to clue us in whether it's a function or not. And what we're looking for is repeated numbers. Do we have any repeats in the domain? Our answer is no. So that means yes, this is a function. Why? Because there are that should say no. No, let me just rewrite this. No repeated x values. And we are happy about that. Now, the second problem, same thing, except for now instead of a table, we're given a list of ordered pairs. So remember, domain is x, and our domain is the x coordinate of each of these points. I'm going to make a list. -4, -2, 0, 2, and 4. I'm going from smallest to largest. And there are no repeated x values. Now we can do the same thing for our range. This is y. We've got 8, 4, 1, 4, and 8. So I've already got an 8 and I've already got a 4. And I'm going to put it from smallest to largest. So I'm going to do 1, 4, and then 8. So that list gets a little bit smaller. We got to ask ourselves, is this a function? When we're classifying that, we only care about the domain. Are there any repeated values in our domain? No. So we can classify, yes, this is a function. Why? There are no repeated x values, which we know is a fancy way of saying the domain. Now we're going to talk about something called function notation. So when we're given an equation, function notation is somewhat useful for us when we want to evaluate a problem. This f of x is just the same thing as a y, but it helps us solve problems like this. When we are finding f of -3, that means any place that we had an x, we're going to replace it with a -3. So this x changed into a 3. So this x changed into a 3. And this is something that I like to go ahead and simplify in my calculator. I always use parentheses when I plug in a number, and I simplify. My answer is -21. You can think of the -3 as the input, and the -21 is the output. We can do the same thing for our next equation over here. We're finding f of -3, so that means I'm going to keep -2 the same. My x is going to change into a -3, and I'm subtracting 11 this time. So our input was -3. I'm going to type this directly into my calculator. I've got -2 times -3 minus, why did I do 100? -2 times -3 minus 11 equals -5. So my input was -3. My output was -5 because we had a different equation this time. We had different numbers we were dealing with. So that's function notation, and we'll see that kind of throughout the rest of Algebra 1. The next problem wants us to graph this equation right here, f of x equals 1/2 x plus 5. We can graph this just as if this was like our y value. Now this is in slope-intercept form, y equals mx plus b, so we can identify the y-intercept and slope just by looking at this equation. Remember that our slope is m, which is the number out in front of x. Our slope is 1/2, and our y-intercept is b. So the number that is represented by b is a positive 5. With those two values, we can go ahead and graph our equation. My y-intercept is the first point that I'm going to plot. So I'm going to go up 1, 2, 3, 4, 5, and put a point. Remember, this is rise over run, kind of how we classify our slope. I'm going to rise 1, and I'm going to run 2. I'm going to rise 1 and run 2. I can go to the left of my intercept, but I'm going to go backwards. I'm going to go down 1 to the left 2, down 1 to the left 2. And once I gather enough points, I'm going to draw my line connecting them. And this is my graph of this equation right here. Something that we can classify an equation by a little bit different. We can classify the domain and the range as an inequality. We know we can think of the domain as the inputs. So if we're given the inputs and the numbers that we can put into our equation, the range, what we want to find is going to be our outputs. And this is where function notation is going to come in handy. We are going to input my two values of my domain, and I'm going to classify my range with what their answers are. So my equation here, f of x equals 4x plus 5, I'm first going to find f of 0, which means I'm going to take 4 times 0 plus 5, and that is going to result in 5. So the low end of my range, I'm going to put a 5. And I'm going to put less than or equal to y. And then I'm going to find my output when I plug in 50 into my equation. So that's going to be 4 times 50 plus 5. And this one I'm going to use my calculator for. Let me put it over here. 4 times 50 plus 5. That equals 205. So that's my largest y value that I can have. These are kind of like the minimum and the maximum values. But I just plug both of those into my equation, and I write my inequality kind of like this expression that was given to me. Range is my y values, which is why I used y. Now, we can relate our relations and functions to an arithmetic sequence. So a sequence is just a list of numbers, and we want to be able to identify any patterns within them. So I'm given 4, and I go to 8, and then go to 12, and go to 16. D is what we call the common difference, and that's the pattern or the change that we see in the numbers. To go from 4 to 8, I added 4. To go from 8 to 12, I added 4. And to go from 12 to 16, I added 4. So my common difference is going to be 4. And what we can do with this is write what we call the explicit formula, which the template is given to us right here. The only other thing we need to know to write our formula is this A1 value, which we can classify as our first term. So the only two things that we have to plug in are this A1 and this D. So we're going to write our equation here. AN equals A1. What's the first term of our expression? Well, it's 4. So I'm going to have 4 plus D, which was also 4, which is a coincidence, times N minus 1. And this is my explicit formula. We can do things with that explicit formula, but right now we're just going to practice writing them. So for my second sequence, I'm going to write a little space for me to find A1. And I'm going to try to identify the pattern again here. What do I have to do to go from 24 to 18? Well, this time I'm subtracting a number. My number is decreasing. I'm subtracting 6. From 18 to 12, I subtract 6. From 12 to 6, I subtract 6. So my common difference here is negative 6. A1, my first term, is 24. So when we write our explicit formula, we're going to have 24, and we're adding to that d, which is negative. So I'm going to put it in parentheses right now because negative numbers can get a little tricky. And then I'm just having n minus 1 at the end of my problem. I'm going to simplify this one more time because when I'm adding a negative number, that's just the same thing as subtracting. So I'm going to turn this into 24 minus 6 times n minus 1. And this is my explicit formula. If we flip our paper over, now we're going to go into kind of some scatter plots and lines of best fit. The first thing we want to be able to do is classify our data, whether it has a positive, negative, or really like no correlation. So that's going to be if I were to kind of sketch a line that follows the trend of the data, is the slope of that line positive or negative? And in this case, this one is positive. So we would say it has a positive correlation. And we can see, I think this was kind of supposed to be over here, but we can see this one, if we draw like a line of best fit, it is heading down. It has a negative slope. So it has a negative correlation. Now, sometimes our correlation can be strong or weak, but we'll talk about that in just a second. Another thing we want to be able to do is interpret a problem based on a line of best fit. So this says, for the trend line, what would the expected temperature be after 2 hours? So I got to find my line, or use my line, and find when my time would be 2. So I'm going to go over here, and I'm going to trace my pencil up till the point reaches, or my 2 value reaches my line. So I'm really asking myself, what would be the y value at that point of my function? And this is going to require us to be like an estimation, because we have the point 50 and then 60. We know that this would be 55, and we're right above that a little bit. So what would my expected temperature be? I feel like a reasonable answer would be 56, a little bit above. And it doesn't give me the units, but I'm just going to say 56 degrees. Potentially it could be Fahrenheit, but it also could be Celsius. It wasn't given to us there. The next thing we can classify or like use to classify data is something called the correlation coefficient. And this is kind of what I was talking about, where we can have a really strong relationship in our data, where sometimes our data points are a little bit weak. And what the correlation coefficient does is kind of measure how far our points are typically from our line of best fit. So if we look at this, these points go through our line of best fit really well. So this is a strong set of data. And when we have strong data, our number is closer to the 0, or closer to 1 or negative 1. And when we have weak data, see how this one's a little bit further out from our line? Our number is closer to 0. So the sign of the correlation coefficient is going to tell me that this is a negative correlation. The sign over here, this one's positive, so we know that it is a positive correlation. But the closer it is to 1, 0.7 or 0.97 is really close to 1. So we're going to classify this as a strong negative correlation. And this one is 0.02976. This is closer to 0. So we're going to classify this as a weak positive correlation. So the sign lets us know whether we can write negative or positive, and the number lets us know whether it's going to be weak or strong. And last but not least, we can write a line of best fit for a set of data. And what we're going to do is use slope-intercept form, which is what we use kind of on the front side of our paper. Let's remember it's y equals mx plus b to help us you find the line of best fit for this data. We could turn this into a scatter plot and like draw the line in there, but we can do it the same with just identifying the slope and the y-intercept. When we are finding the slope, we have to remember the slope formula. We can find the slope using 2 points. So I'm just going to use the first and the last point here to help me find my slope. I really could choose any 2 points that I want, but I'm just going to do the first and the last. So this number right here, the top number is x. So I'm going to call this x2. This is going to be y2. This one's going to be x1 and y1. And I'm going to plug it into my formula here. y2 is 10,300 minus y1, which is 900, divided by x2, which is 13, minus x1, which is 0. Now, this is something we can simplify using a calculator. And I like to just type everything in how I see it in my fraction. You can do this on Desmos if you needed to. 13 minus 0. My calculator will leave it as a fraction, so I want to turn this into a decimal. So it's 723.07. I think I saw something where it says round to the nearest hundredth with just 2 decimal places. So I'm going to do 0.0. That 6 is going to bump my 7 up to an 8. So I'm going to say M is 723.08, and B, which is my y-intercept, happens when x equals 0. So on my table, do I see any point where x is equal to 0? Well, that's this guy right here, making this 900 value my B. Now let's go ahead and write this as an equation. I'm actually going to write it in function notation. So I'm going to write it as f of x equals m, which is 723.08 x plus b, which is 900. So my equation is this guy right here. And the reason why we like to have a line of best fit, because we can make predictions about the future. I guess 2018 is not the future, but back in the day it was. We want to use our line of best fit to predict gross revenue for 2018. So this X represents the years since 2002. So to find how many years have passed, we can do 2018 minus 2002, which would give us 16 there. So in our equation, I'm going to take 723.08 times 16 plus 900 to find the expected gross revenue. 723.08 times 16 plus 900. This expected revenue is 12,469.28. And I'm going to leave it rounded to the nearest hundredth, the 2 decimal places, because it's money, so 28 cents makes sense. And that's going to be our last problem on our remediation for today. Now you're ready to take your remediation quiz.